Welcome back, curious friends. Today, let's explore one of the most captivating mysteries of quantum mechanics, the Schrödinger wave equation. This remarkable mathematical tool offers us insights into the intricate behavior and movement of tiny particles such as atoms. So, get ready to uncover the fascinating secrets of nature together. It's named after the Austrian physicist Erwin Schrödinger, who first formulated it in 1925, one of the most accurate theories of how subatomic particles behave. The equation is a cornerstone of modern physics and plays a central role in understanding the behavior of particles at the atomic and subatomic levels. The Schrödinger equation describes how wave function changes with its time. It's akin to understanding how a wave propagates or evolves over time. As you're familiar, Newton's second law applies to visible large scale objects such as cars and balls, elucidating how they move and behave. But how to understand the motion and behavior of quantum particles? Understanding the motion and behavior of quantum particles requires a different approach than classical mechanics. In quantum mechanics, the Schrödinger equation plays an important role, and the Schrödinger equation helps us understand how things move. They are like different games with different rules. Newton's law is for macroscopic things we can see, like cars and balls, while the Schrödinger equation is for the tiny invisible particles like electrons that make up our world. The Schrödinger equation is a fundamental equation in quantum mechanics that describes how the quantum state of physical system changes over time. It can be understood from an example like this. Imagine you have a toy car. When you push it, you know it goes in a certain direction, right? That's following Newton's law. It helps us to predict where things will go when we push or pull them. It's like a map for how things move. Now, let's talk about the Schrödinger equation. Imagine you have a magic bubble around the toy car. Inside this bubble, the car can be in different places at the same time. The Schrödinger equation helps us to understand where the car might be inside the bubble. It's like a special picture that shows us all the possible places that car could be in. The Schrödinger equation provides a way to calculate the wave function of a system and how it changes dynamically in time. However, the Schrödinger equation does not directly say what exactly the wave function is. Schrödinger's equation shows all of the wave-like properties of matter and was one of the greatest achievements of 20th century science. His equation was based on the principles of de Broglie wavelength, which tells us that small stuff like electrons can act as waves, not just tiny particles. Louis de Broglie figured this out in 1924, showing that even the tiniest things can act like waves, similar to light. Learning about this helps us explore the small world of atoms and electrons, which is really important in science. The Schrödinger's equation is a fundamental equation in quantum mechanics that provides a mathematical representation of a dual particle-like and wave-like behavior of atomic and subatomic particles. The solutions to this equation, known as wave functions, give probabilities of where a wave particle might be found. The equation has two forms, the time-independent Schrödinger equation and the time-dependent Schrödinger equation. The time-independent Schrödinger equation, TISE, helps us find the fixed states and energy levels of quantum systems, while the time-dependent Schrödinger equation, TDSE, tells us how these states change over time. These equations are the basis of quantum mechanics, allowing us to understand and predict how quantum systems behave. Schrödinger equation is fundamentally a differential equation and it draws a link between the energy of a particle and the probability wave of the particle. The solutions of this equation, also known as wave functions, can give you the probabilities of where a particle might be found, a concept known as a probability distribution. For example, if you were to apply the Schrödinger equation to an electron in an atom, the resulting solution would give you an orbital, a spatial description of where you are most likely to find the electron. As a result, the Schrödinger equation plays a key role in predicting and calculating the behavior of particles in quantum realm. For instance, you might have seen images of p orbitals and s orbitals in chemistry textbooks. Those beautiful cloud-like shapes are visual representations of wave functions derived from the visual representation. Those beautiful cloud-like shapes are visual representations of wave-like functions derived from the Schrödinger equation. So, while the Schrödinger equation helps us understand how things change over time, the equation essentially states that the change in quantum state with respect to time is proportional to the kinetic energy operator and the potential energy of the system. The Hamiltonian operator, representing the total energy of the system, is a key component of the Schrödinger equation. It includes kinetic energy and potential energy terms. The equation essentially states that the time rate of change of the wave function is proportional to the energy of the system. The Schrödinger equation is a complex valued equation, meaning it involves imaginary numbers. In quantum mechanics, the wave function describes the state of a quantum system. However, it doesn't give us definite answers like in classical physics. Instead, it provides probabilities for different outcomes when we measure properties like position, momentum, or energy. This means we can't predict exactly where a particle will be, but we can calculate the likelihood of finding it in various places. So, rather than deterministic predictions, quantum mechanics gives us a statistical probability. However, in many cases, exact solutions are not possible, and researchers rely on approximation methods and numerical techniques. Two primary factors influence the behavior of a particle's wave over time, as indicated by the Schrödinger equation, are energy. The total energy of the particle affects how its wave function evolves over time. This includes both its kinetic energy, how fast it's moving, and its potential energy, how it's influenced by its surroundings. Environment. The surroundings or environment of the particle characterized by the potential energy function. So, by understanding the particle's energy and the environment, we can predict how its wave function will change over time. This is essential for describing the behavior of particles at the quantum level and its foundation of quantum mechanics. It is used in physics and most of the chemistry to deal with problems about atomic structure of matter. It is an extremely powerful mathematical tool and the whole basis of wave mechanics. You would use the time-independent Schrödinger equation to solve for the wave function and energy levels of particles. It has been used to calculate a wide range of properties of quantum systems, including their energy levels, like electronic structure, and their optical properties. In summary, the Schrödinger wave equation serves as our gateway to comprehending the intricacies of quantum world. Thank you for watching. Please remember to like, share, and subscribe to my channel for more content like this.